All right, hello everybody, last one for the household. In the last video we got these three first order conditions that I wrote up here. Oops, I don't have my pen on. Okay, close this. So these three up here. And now we want to combine them to get some equations that have some economic meaning. So the first thing we're going to tackle is this one, and we're going to solve for lambda. Now, a good question you should ask is, well, why should I pick this one to solve for lambda and not pick this one here? Because I could solve, I could use either of these to be lambda. And the answer is you just need to know that we want to think about shadow prices in terms of consumption. Because we think about investment as a way to move consumption through time. We don't think about the investment as a way to move leisure through time. Although you can think of it that way. That's kind of what this equation is saying here. But we always think about time in terms of consumption. And so we choose this equation. Okay, so with that said, we will choose this one as our lambda. And we're going to put these two together. So we'll end up with Ct to the minus sigma c divided by Pt is equal to Lt to the sigma L divided by Wt. And let's take the prices to this side and take the consumption to this side. And why am I drawing this up? Because there's a minus sign here, right? So you could also write this as 1 over Ct sigma Cpt equals Lt sigma L over Wt. So I'm going to put Wt right here, and I'm going to put Ct right here. Okay, so we get Lt sigma L, Ct sigma C is equal to Wt over Pt. So this is our first box, and you should know this equation. You should recognize that this equation is the labor supply curve. The labor supply curve. Okay. Why is this the labor supply curve? Because it's pinning down the wage as a function of labor. And in particular, we want to focus on this term on the left. And if you go back to our utility function, our intra-temporal utility function, which was this one, Ct to the 1 minus sigma c over 1 minus sigma c minus Lt 1 plus sigma L over 1 plus sigma L. You'll see that if you take dut dct will be this term, 1 over this term. And if you take, so that will be Ct to the minus sigma c. And if you take dut dlt, that will be just Lt sigma L. And so if you take the ratio of these, dut over dlt divided by dut over dct, that will be exactly Lt sigma L, Ct sigma c. Okay, so you see that this term that we highlighted, well, I'm going to keep this term right here, is the marginal rate of substitution between consumption and leisure. Consumption and leisure. Okay, so the wage, what this tells us is that the wage is going to be set such that the household is indifferent between working and working, right? Working to get some money to consume or resting. So this is the labor supply curve. And it's in real prices, right? So we're dividing, this is like big Wt. We haven't done the Walras's law yet. So this is big Wt. So we have real prices is going to be equal to the marginal rate of substitution between labor and consumption. Leisure and consumption, well, labor and consumption, same thing. Okay, so this is our first box. This is an important equation, and you should know that it gives the labor supply curve. And why does it give the labor supply curve? Because it gives us this marginal rate of substitution. And also, this is a general result. It looks like this because we had a CRRA function, but no matter what, when you solve this model, if you change the utility, you'll always have the marginal rate of substitution here, and you'll always have the real wages here. Okay, so that's that. We can sort of delete this sidebar. We'll keep our boxed equation. And next we need to deal with the Euler equation, which comes from our last thing we have here, this last answer that we boxed. We have lambda tpt equals beta lambda t plus 1, 1 minus delta pt plus 1 plus r t plus 1. And here's where we need to know that this is the one we're going to use for lambda. And again, because we want to think about consumption moving through time, we don't want to think about leisure or labor moving through time. So, excuse me, let's plug that in. So we'll get CT sigma C over PT times PT is equal to beta CT plus 1 over PT plus 1 sigma C. Now here, there's another important point that the rules we derive, the relationships we derive for any variable, for C, for L, for lambda, are true for all time. Okay, so if you find here that lambda t is equal to CT over PT, and it'll also be true at t plus 1, t plus 2, t plus 3. You can just increase these, you can increment these indices. So that's what we did here. We incremented the indices and replaced it. And then we're going to have 1 minus delta pt plus 1 plus rt plus 1. So this cancels. And we would like to write this correctly. There's a minus sign here and a minus sign here. So let's put the CTs together. Put them over here. And we can factor this pt plus 1 in here. Yeah, so that'll cancel. And then we'll get real rentals over there. So we're going to have CT over CT plus 1 to the minus sigma C is equal to beta 1 minus delta plus RT plus 1 over PT plus 1. Close parentheses. Another side note, I have been sloppy and lazy, and you should be more careful. There should be expectation signs everywhere here, right? Everything here is expected. Why? Because none of these are state variables. Or excuse me, none of these sorry, what's my explanation? Sort of none of these are state variables, yeah. These all come from, these plus 1s come from the Lagrange problem, right? We stepped forward the Lagrangian, and the Lagrangian, I mean, going all the way back to the utility, that should all be expected. We saw at the very beginning that utility at time t is equal to the expectation at time t of the sum from s equals 0 to infinity of little u t plus s. Okay, and whenever we step forward, we're putting an expectation over everything. And the only thing that we know in the future is kt, because we have a law of motion of capital for this. So if we take a kt minus 1 and turn it into a kt, that's not expected because we have an equation for that. But if we take it one step further, that is expected because we don't know what is it plus 2. We'd have to have an expectation in there. But yes, everything, there should be expectations. Yeah, I mean, expectation here, okay? Be careful with this. Just be, yeah, I'll make sure when we do another problem to be very clear about this, but just be aware that except for KT, because we have an equation that moves it through time, we maybe don't need an expectation there, but everything else we need expectations. Okay, so we're done. I mean, this hits the box. But I guess the only thing we could do is we could maybe flip this over. This minus sign could come inside, right? And so we could write this as the expectation at time t of CT plus 1 divided by CT is equal to beta times 1 minus delta plus the expectation at time t of r t plus 1 divided by pt plus 1. Okay, and this gets a box. And again, you should know this equation. You should know the name of this equation. This is the Euler equation. The Euler equation. And what does it tell you? It tells you about the trade-off between consumption tomorrow here and consumption today. Okay, so what you need to pay the household to give up 1 unit of consumption today in order to have 1 unit of consumption tomorrow is this. And it should make some sense, because how do you move consumption through time? You move consumption through time via investment. So to shift this consumption, the household needs to be compensated in terms of RT plus 1 in real terms. And it's scaled by the depreciation rate. So the household is always losing its wealth, so it has some incentive to shift forward because it needs to replace that. And then also it's scaled by this beta. If it cares less, about the future, then you have to pay it less to shift through time. Okay. So there you go. We have 2 equations. We have the labor supply curve, check, and we have the Euler equation, check. So what would you write down on your answer sheet? Well, you'd write down the labor supply curve, you would write down the Euler equation, and you would remember to write down the laws of motion of capital. So if we just make some space here, what do we need to box? Remember, we boxed the first order conditions, which we have 2 of them here. We also box the budget constraint. Okay, so PT CT plus IT equals RT KT minus 1 plus WT LT. We put a box around this one, and we put a box around the law of motion of capital. 1 minus delta KT minus 1 plus IT. Okay, so now we have 1, 2, 3, 4 equations. So these are our first 4 equations, moving towards a system of equations that will perfectly describe, that will pin down all of the variables in the model at any time t. Okay, so the household is done, and in the next video we're going to turn to the firm. So I'll see you there.